Welcome to this explainer. Today, we're going to completely shift your perspective on a topic that, honestly, probably brings up some slightly painful memories of rote memorization and endless mathematical formulas. Yeah, we're talking about trigonometry. But we're taking it off the chalkboard and bringing it straight into the physical world. By the end of our time together, you won't just remember sine and cosine. You're going to be able to physically visualize them as incredibly simple, elegant spatial tools. Let's get right into it. Okay, let's dive into this. What do sine and cosine actually mean? I mean, for so many of us, they were just mysterious little buttons on a calculator or abstract functions we had to cram into our brains for a math test. But what if I told you that they're fundamentally just coordinates? They are literally the purest way to describe where you are in a two-dimensional space. Our goal right now is to completely demystify these terms once and for all. Section 1. The unit circle intuition. Spatial building blocks. We're going to start with the unit circle. I want you to imagine a perfectly round track, and the distance from the exact center of that track to the outer edge is exactly 1. It could be 1 meter, 1 mile, 1 arbitrary unit. It really doesn't matter, as long as that radius is 1. Now picture a single dot, just a point, moving along the edge of this circle. This super simple environment, this unit circle, is the foundational physical space for literally everything we're about to discuss. As that point moves around our unit circle, it creates an angle, which we usually call theta. But more importantly, at any given moment, that moving point has the very specific location. It has a horizontal position and it has a vertical position. And guys, that is literally all sine and cosine are. Cosine is just your horizontal position. It's your x-coordinate. In sine, it's simply your vertical position, your y-coordinate. That's it. They're just a complementary horizontal and vertical duo working together.
Section 2, Mapping Key Angles, Tracking Anchor Points.
Let's move to and see how this builds chronologically as we travel around our circle. At 0 degrees, we are at the starting line, fully to the right. So our horizontal position, our cosine, is a perfect 1, and our vertical sine is 0, right? Because we haven't gone up at all. Now, drive that point up to the very top at 90 degrees. We are fully up, so our vertical sine is exactly 1, and the horizontal cosine shrinks to 0. Swing on around to 180 degrees, and now we're fully to the left. Horizontal is -1. Dive down to the bottom at 270, we are fully down, making the vertical sine -1. And finally, at 360 degrees, we've traveled the whole track, right back to the start. You see? These ones and zeros, they aren't just abstract math numbers, they are exact physical locations. Section 3. A simple memory trick. Horizontal versus vertical. I know keeping X and Y straight can sometimes feel a bit tricky, so let's lock this concept into your memory using a physical motion. Now, what's really interesting about this slide is a simple phrase. Cosine comes first horizontally, sine rises vertically. If you ever catch yourself second-guessing which is which, just pause and repeat that out loud. Cosine lays the flat groundwork. It's the horizon. It comes first. Sine is what stands up on top of it. It rises vertically. Section 4. Sine and cosine as projections. Active functional tools. Think of sine and cosine as projection tools. This is where things get really fascinating. You see, when you have a single direction, what we in the math world call a vector, it can be honestly kind of hard to work with if it's pointing off at some weird random diagonal angle. Sine and cosine act as a pair of scissors. They allow you to split that one single complicated direction into clean, perfectly manageable components. They literally tell you exactly how much of that direction lies along the flat horizontal axis and exactly how much lies along the straight vertical axis. They break apart the complex into the simple. So the crucial point is how we actually scale this up. What if our track is bigger than a radius of just 1? What if our vector has a much longer length, which we'll call r? Well, the formula here is just beautiful in its simplicity. To find your exact horizontal x position, you just take your total length, r, and multiply it by the cosine of your angle. Easy, right? And to find your exact vertical y position, you multiply that same r by the sine of your angle. It's essentially just a projection scale. It takes that unit circle intuition we just learned and stretches it perfectly to fit absolutely any distance. Section 5, Navigating the Real World, GNSS and Beyond. And this brilliantly illustrates why this matters right now in your everyday life. In Global Navigation Satellite Systems, or GNSS, basically the GPS on your phone, this exact logic is quietly running in the background. When you need to know exactly where you're going, your navigation system treats cosine as the indicator of how much you are moving in the x-axis, the east-like direction. Meanwhile, sine is constantly calculating exactly how much you're moving in the y-axis, the north-like direction. Together, these two incredibly simple projection tools combine to perfectly map out your precise heading on the globe. It kind of completely changes how you look at navigation, doesn't it? These aren't just frustrating high school math formulas to memorize and forget. They are literally the fundamental coordinates of space and movement. So next time you pull up a map on your phone or you're following a GPS route, ask yourself, how are sine and cosine projecting your path right in that exact moment? Keep that spatial awareness with you, and I promise, the math will absolutely never look the same again. Thanks for joining me on this explainer.